Hi, and welcome back to my series of videos for Physical Chemistry 1. One question that we never answered when we talked about equilibrium is, why are some chemical reactions irreversible, but others are reversible and can occur in both backward and forward directions? As we'll see today, the Gibbs free energy can give us an answer to that question. You might recall that when we were learning about Gibbs free energy in the last video, we saw that a reaction is spontaneous when delta G is less than 0, and non-spontaneous when delta G is greater than 0. That means that the reaction will proceed in the forward direction when delta G is a negative number. When delta G is positive, the reaction is non-spontaneous, but that doesn't mean that no reaction is possible. Instead, the reaction is spontaneous in the reverse direction. So, for example, here's a chemical reaction with a positive value for the Gibbs free energy. Because delta G is non-spontaneous, the forward reaction can't occur unless we put energy into the system. However, the reversed reaction does happen spontaneously. Also, as you might remember from the last video, when delta G for a reaction equals 0, the reaction is at equilibrium, so the forward and reverse reactions happen at the same rate. It turns out that if delta G is between positive and negative 5 kilojoules per mole, then the reaction is reversible. For example, here's the reaction in which methanol vapor becomes a liquid. If we calculate the Gibbs free energy for this reaction, we find that it's negative 4.4 kilojoules per mole. It's a negative number, which tells us that the reaction happened spontaneously. That makes sense. Methanol is a liquid at room temperature, so it makes sense that the right side of the equation is more favorable. However, notice that the Gibbs free energy is between positive and negative 5 kilojoules. That means the reaction is reversible. That also makes sense. If you've ever worked with methanol, you know that it evaporates very quickly, so there is an equilibrium between the two sides of the reaction. In other words, a significant portion of the methanol molecules will be in the gas phase, even if the liquid phase is more favored. Here's another example in which iodic acid dissociates to form aqueous hydrogen and iodate ions. The Gibbs free energy of this reaction is positive 4.39 kilojoules per mole. Like the previous reaction, this reaction has a delta G between positive and negative 5 kilojoules, so this is a reversible reaction. But unlike the previous reaction, delta G is positive, so this reaction isn't spontaneous in the forward direction. Instead, the reaction favors the reactants, so the reaction is spontaneous in the reverse direction. On the other hand, reactions that have a Gibbs free energy greater than positive 5 kilojoules or less than negative 5 are irreversible. For example, the combustion of methane is definitely an irreversible reaction. We never expect to see the carbon dioxide and water recombine to reform methane and oxygen. And when we calculate delta G, we find out that it's negative 800.8 kilojoules per mole. That's way outside the range that we'd get for a reversible reaction. It's a large negative number, so the reaction is irreversible in the forward direction. Here's another reaction we've seen before. Solid silver chloride dissociates to form aqueous silver and chloride ions. Delta G for this reaction is positive 55.62 kilojoules per mole. This is another irreversible reaction, but this one has a positive Gibbs free energy, so it's irreversible in the reverse direction. That makes sense for this reaction. Silver chloride is usually considered to be an insoluble compound, and this is why. Very little of the ions will exist in this system because the solid silver chloride reactant is heavily favored by the Gibbs free energy. So, as you can tell, there's a definite connection between the Gibbs free energy and equilibrium. The exact relationship between them was determined by Josiah Gibbs. He figured out that the two are related by this equation. In this equation, delta G is the Gibbs free energy. This quantity is called the standard Gibbs free energy. That means it's delta G measured at standard temperature and pressure. Let's see what we can do with this equation. A little earlier we saw this reaction. Suppose we perform the reaction at 100 degrees Celsius and take measurements when it's not at equilibrium yet. Instead, we find that we have concentrations of 0.100 molar iodic acid, 0.0300 molar hydrogen ion, and 0.0800 molar iodate ion. If we plug those into the formula for Q, we get a Q of 0.240. We'll plug that into our equation along with R. The temperature is 100 Celsius, which is 373.15 Kelvin. Finally, we mentioned a little earlier that delta G at standard temperature is positive 4.39 kilojoules per mole. Since our value for R contains joules in its unit, we should convert our data for delta G into joules too, so it's 4,390 joules. When we perform the calculation, we get negative 7,180 joules. What does that tell us? Well, the Gibbs free energy is large and negative, so it's telling us that at this temperature, when we have these concentrations for the compounds in the reaction spontaneously goes to the right. So, this is a very useful equation. Using it, we can determine whether or not any chemical reaction will occur at a given temperature. All we have to know is the concentrations of the compounds and the standard Gibbs free energy. Since we know the standard delta G for hundreds of different compounds, that means we can predict whether or not thousands of different reactions are possible. But there's another useful thing we can do with this equation. It turns out that if we know the standard Gibbs free energy for a reaction, we can figure out its equilibrium constant, or vice versa. Here's how. As you might recall, at equilibrium the Gibbs free energy is equal to 0. So if the reaction is at equilibrium, we can set the left side of this equation equal to 0. Also, if we're at equilibrium, the reaction quotient Q is equal to K, the equilibrium constant for the reaction. If we move the standard delta G to the left side of the equation, we get this. As you can see, if we know delta G, we can figure out the equilibrium constant, or vice versa. Let's try it. Suppose we perform the reaction in which carbonic acid reacts to form water and CO2 at 25.0 degrees Celsius. What will be the equilibrium constant? We'll use the equation we just talked about. All we need is the standard delta G, which we can figure out using Appendix C and this equation. When we look up the values of delta G, we find that water is negative 237.13 kilojoules per mole, CO2 is negative 394.4, and carbonic acid is negative 639.7. That gives us a delta G of 8.17 kilojoules per mole. We'll plug that into our equation, along with R and the temperature, which is 298.15 Kelvin. Remember, R uses joules in its unit, not kilojoules, so we need to convert our value of delta G to joules too. Now we just solve the equation. First, I'll multiply R and the temperature. Next, I'll divide both sides by negative 2,749 joules per mole. Finally, we get rid of the logarithm by making the left side the exponent on E. That gives us a result of 0.0370 for K. That probably seemed like a pretty ordinary calculation, but it's actually a really impressive accomplishment. That's because we just figured out the equilibrium concentration of a reaction without having to know anything about the concentrations of any of the compounds in the reaction. We've never been able to do that before. And that's a very useful tool we now have. We can figure out the equilibrium constant for any reaction without ever having to perform a measurement in the lab, as long as we know delta G for the reaction. And this calculation can also be used in reverse. If we know the equilibrium constant, we can determine delta G for a reaction. For example, suppose we want to know more about the reaction in which benzoic acid dissociates in water at 50.0 degrees Celsius. The equilibrium constant for that reaction is 6.31 times 10 to the negative fifth power. From that, we can determine the standard delta G for the reaction. It turns out that when we perform the calculation, we get positive 25,980 joules per mole. Or, using significant figures, we find that delta G is positive 26.0 kilojoules per mole. It turns out that the details of equilibrium are crucial to understanding lots of topics in biology and chemistry, like acids and bases. If you've taken a biology class, you may also have talked about homeostasis, which is the idea that the physiology of a living thing tends to want to be stable. So, for example, your body temperature, the pH of your blood, and the amounts of ions and sugars in your body fluids tend to stay within a certain range as long as you're not sick. To understand why that happens, we really need a deep understanding of how equilibrium works. So let's get back to our discussion of equilibrium. We've seen that we can write concentrations of compounds in a reversible reaction in this ratio, and that the ratio always has the same value at equilibrium, called K, the equilibrium constant. Let's see what else we can do with that. Suppose we're studying this reaction, and at equilibrium we have 0.0010 molar CO2, 0.15 molar hydrogen ion, and 0.15 molar bicarbonate ion. What's the equilibrium constant? This is a problem we already know how to solve. We just need to write out the equilibrium expression, which is products over reactants, each raised to the appropriate power. We saw several examples like this in the previous two videos, so you might want to watch those if you haven't already seen them. If you did see those videos, you know that we don't usually include pure liquids or solids in the equilibrium expression, so we'll leave water out of our formula. That means we have CO2 in the numerator and hydrogen and bicarbonate ions in the denominator. We can plug in the concentrations we were given in the question, and when we solve the formula, we get a value of 0.044 for K. Now let's try something we haven't done before. Suppose we do this reaction again, but this time we start with different amounts of each compound. After a while, we measure the concentrations and find that we have 0.030 molar CO2, 1.8 molar hydrogen ion, and 2.5 molar bicarbonate. Is there any way for us to know whether the reaction is equilibrium yet? You might think that the answer is obvious. The concentrations are all different than they were in the previous problem, so that might make you think it must not be at equilibrium. But remember, at equilibrium, what's important is not the exact concentration of each compound. What matters is the ratio. So we'll calculate this ratio again. From the last problem, we saw that the ratio has a value of 0.044 at equilibrium. If that's what we get when we plug in our new values, then we'll know the reaction really is at equilibrium. So let's try it. We plug in our new values, and when we solve the formula, we get a result of 0.0067. This is certainly not what we got for K last time, so the reaction is not at equilibrium. When we solve the ratio of concentrations for a reversible reaction, but we're not sure whether or not it's at equilibrium yet, we shouldn't call it K. K is only the ratio when the reaction is at equilibrium. If we're not sure whether it's at equilibrium, we call it Q instead, and Q is called the reaction quotient. So, if Q has the same value as K, then the reaction is at equilibrium. In our example, Q was less than K. That means that the concentrations of the products will need to go up in order to make Q increase until it eventually becomes equal to K. In other words, the reaction will need to shift to the right in order to produce more products. So, if Q is less than K, the reaction will shift to the right. The opposite is true if Q is greater than K. In that case, we'd have too much product, and we'd have to decrease the amount of product in order to reach equilibrium. So that means the reaction would shift to the left. And if Q is equal to K, that means we're at equilibrium, so the forward and reverse reactions would be happening at the same rate. The connection between the equilibrium constant and the Gibbs free energy allowed the Dutch chemist Jacobius van Hoff to derive one more very useful equation. From the previous video, we have this equation for the standard Gibbs free energy. And from video 28, we also had this one. If we set those two equations equal to each other, we get this. Let's solve for the logarithm of k by dividing both sides by negative RT, which gives us this equation. Now, suppose we perform a chemical reaction twice, once at a temperature T1 and once at a different temperature T2. In that case, we could write this equation 2 times, once for each experiment. We'll call the equilibrium constant kT1 for the first experiment and kT2 for the second. Now, let's subtract one equation from the other. If we do, that gives us this result. We can simplify this equation quite a bit. First of all, remember the difference between two logarithms is just equal to the quotient of the terms we're taking the logarithm of, so we can rewrite the left side this way. Next, notice that the terms containing the entropy on the right side will cancel out, so we can drop them from the equation. Finally, let's factor negative h0 over r out of the remaining terms. That leaves us with this equation, which is called the Van Hoff equation. It's a very useful way to determine the standard enthalpy of a reaction. Or, if we already know the standard enthalpy, we can predict how the equilibrium will change with the temperature. For example, here's a reaction we saw in the previous video. Suppose we wanted to know what the equilibrium constant of this reaction would be at 139 degrees C. From the work we did in the previous video, we know that K is 1.83 times 10 to the minus 5 at 25 degrees Celsius. We'll need to convert the two temperatures into Kelvin. Once we do that, we can plug the temperatures into the Van Hoff equation. We also need to determine the standard enthalpy. If we use a table of data for the products and reactants, we can subtract the delta H for the products minus reactants and find out that delta H0 is negative 197.9 kilojoules per mole. We need to convert that to joules per mole, but once we do, we can plug that into our equation too. Now we just solve for the equilibrium constant. It turns out that the right side of the equal sign is equal to negative 22.08. Next, we eliminate the logarithm by raising e to the right side of the equation, which gives us 2.568 times 10 to the negative 10. That finally gives us a value of 4.70 times 10 to the negative 15 for the equilibrium constant at 139 degrees C. Notice that this is much lower than the equilibrium constant at 25 C, which means that at the higher temperature, the reaction is shifted to the left. It turns out this is exactly what we'd expect for an exothermic reaction like this one. And we'll see why in the next video, where we'll talk about one more topic related to equilibrium, Le Chatelier's principle. It's a fun topic to end the course on, and it's one you probably heard about when you took general chemistry, so I hope you'll join me for that. Until then, have a good week.